Neutron stars are some of the most extreme objects in the universe. They are not planets, not quite stars, and not black holes, but something far stranger. In many ways, they are giant atomic nuclei, floating in space, born from the violent deaths of massive stars. To understand how something so bizarre can exist, we have to begin with how stars live and how they die. Stars are enormous spheres of hot plasma, held together by gravity and powered by nuclear fusion. Deep in their cores, hydrogen atoms are crushed together, fusing into helium and releasing vast amounts of energy. This energy pushes outward, balancing the inward pull of gravity. As long as this balance exists, a star remains stable, shining for millions or even billions of years. But no star lives forever. When a massive star, many times heavier than our sun, runs out of hydrogen fuel, the balance begins to fail. Gravity slowly gains the upper hand. The core contracts and heats up, igniting new fusion reactions. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. And then the process stops. Iron is a dead end for fusion. Unlike lighter elements, iron does not release energy when fused. When the core fills with iron, the outward pressure from fusion suddenly vanishes. In a fraction of a second, gravity takes complete control. The core collapses catastrophically. The pressure becomes so intense that electrons are forced into protons, combining to form neutrons. This process releases a flood of neutrinos and transforms the core into an object made almost entirely of neutrons. What was once a core larger than Earth is crushed down into a sphere only about 20 to 30 kilometers wide. This is the birth of a neutron star. A neutron star contains more mass than the sun, compressed into a volume the size of a city. Its density is so extreme that a single teaspoon of neutron star matter would weigh billions of tons on Earth. In fact, all of humanity could fit into a sugar cube-sized piece of neutron star material. This is why neutron stars are often described as giant atomic nuclei. In an atom, protons and neutrons are packed tightly together in the nucleus, surrounded by a cloud of electrons. In a neutron star, gravity has crushed matter so completely that the distinction between individual atoms disappears. The entire star behaves like one massive nucleus, held together not by electromagnetic forces, but by gravity itself. The surface of a neutron star is just as extreme. Newly formed neutron stars can reach temperatures of over 1,000,000 degrees Celsius. Their gravity is so strong that light leaving the surface is bent, allowing an observer to see parts of both the front and the back of the star at the same time. If you were standing on a neutron star, a fall of just 1 meter would be enough to smash every bone in your body before you were pulled apart, atom by atom. Inside the neutron star, matter exists in forms we cannot recreate on Earth. The outer crust is a solid lattice of crushed atomic nuclei, immersed in a sea of electrons. Deeper down, gravity squeezes nuclei so tightly that protons and neutrons rearrange into strange shapes. Long strands, flat sheets, and tangled structures physicists call nuclear pasta. This material may be the strongest substance in the universe. Beneath this lies the core, where physics becomes uncertain. Protons and neutrons may dissolve into their fundamental components, quarks, forming an exotic state of matter unlike anything we have ever observed. Or they may remain locked together in ways we do not yet understand. Neutron stars push our theories of matter to their breaking point. Neutron stars are also cosmic dynamos. As the collapsing core shrinks, it begins to spin faster, conserving angular momentum like an ice skater pulling in their arms. Some neutron stars rotate hundreds of times per second. Combined with magnetic fields trillions of times stronger than Earth's, this creates powerful beams of radiation that sweep through space. When these beams cross Earth, we observe them as pulsars, some of the most precise natural clocks in the universe.